It's my great pleasure to introduce our work. Sorry not being present due to the current situation of the breakout of the coronavirus, and thanks for the support from the CVI committee and my section chair, Professor Fang. My work is related to deep reinforcement learning, titled with Universal Value Iteration Networks when spatially invariant is not universal. First, let's take an example to illustrate the task we worked on. Suppose you are on an interstellar travel. You land on a strange planet. Unfortunately, the condition of the landing caused some error of your spaceship. Your AI assistant tells you you can only navigate through magnetic fields. However, there is no global intrinsic magnetic field on this planet. In other words, the magnetic field varies with the coordinate in the state space, so the transaction kernel also varies with states. This is the main topic of this paper, planning with spatially variant MDP. Now let's talk about some background. In reinforcement learning, a model-free method is learning a value function from experience and selecting an action according to the value function. And the model-based method is learning some knowledge from experience and planning on it to obtain a policy. Literature in neuroscience reports that humans' behavior are generally controlled by both of them. It's intuitive in deep reinforcement learning research to combine the strengths of both model-based and model-free to improve the performance. However, at present, most existing approaches of deep reinforcement learning is model-free. They focus on leveraging the deep neural network structure to approximate the value function. Lack of planning computation as in the conventional model-based approaches, which is critical for long-term reasoning and inference. Value iteration networks propose to include the value iteration process with the CNN to combine model-free and model-based methods. With the value iteration model, VN generates well in conventional navigation domains, showing that the planning computation is beneficial to the applications that require complex long-term reasoning. The strength of VN lies in the exploitation of the resemblance between the value iteration and CNN. However, the use of CNN also limits them to serve in the conventional navigation problems, whose state space can be seen as regular lattices. There are some extensions of VN. They can deal with more tasks than regular lattices, but all of them still use convolution operator. We argue that the use of convolution operators makes them only applicable to the problem set of spatially invariant MDP. We define spatially invariant MDP as follows. An MDP is spatially invariant if and only if there is a function D mapping a state pair to a n-dimensional vector, subject to for any two state pairs. If their D vector is the same, then the transaction probability is the same. For example, in Great Wall Navigation problem, the DSISJ xi minus xj yi minus yj. Obviously, when D vector is the same, the transition probability will be the same. In fact, VN and its extensions implicitly exploit the property of spatially invariant. They use a small convolution kernel to approximate the complete transaction function. In the left, the top one is Bellman equation and the bottom one is the approximate form in VN. The convolution kernel W is used to approximate the transition probability. In Great Wall Navigation problem, the transition model of each state is the same and the convolution operation, the kernel slides across the state space, is an effective way of weight sharing. So VN and its extensions can use a small kernel to approximate the transition model of every state, reduce the parameters greatly. In theory, every MDP can be seen as a navigation problem in state space, but most of them are not naturally spatially invariant. For these tasks, we have two major directions to deal with. First, the perspective of problem, we can try to find a method that determines the proper coordinates of states in 2D space, make it be spatially invariant MDP in new state space. Then we can still use convolution to sharing the weights. Another direction, we can replace the convolution module with more flexible structure to capture the dynamics without the assumption of spatially invariant. The model we proposed, Universal Linear Iteration Networks, is exploring the second pace. The key of UNN is to learn a complex structure for planning computation which can summarize the transaction dynamics and save computational cost of linear iteration. Our contributions are as follows. First, we provide a formal definition of spatially invariant MDP and show that VN and its extensions are computationally bounded to it. Then we propose UVN to deal with spatially variant MDP. Besides, UVN can be seen as an exploration of differentiable programming and a dynamic network. And we formalize Minecraft as a hierarchical task, combine planning, computation, and model-free methods. The experimental results show that our structure is effective. Next, let's talk about UVN more specifically. This is the structure of UVN. In the left, the environment is the two MDPs that we want to solve. The goal of UVN is to learn an embedded MDP which approximates orange MDP in terms of the optimal policy, and then solve embedded MDP via linear iteration and obtain the optimal solution for the original tasks. With the parameterized embedded MDP initialized, the objective function is to minimize the loss between Q value of the embedded MDP and true MDP. As the VI algorithm does not have any non-differentiable operator, the parameters of embedded MDP can be iteratively updated with supervisor signal and backpropagation. To construct the embedded MDP, first we define functions that project the true state and action space to embedded state and action space. Then we leverage a CNN to learn a function fr to convert state to embedded reward function. Then the challenging part is to encode the transaction function. In principle, there are SAS variables in transaction function, but we cannot use so many parameters, or it will cost massive memory and the sample efficiency will be very low. UVN can find the optimal weight sharing structure automatically for various tasks. UVN represents the network structure as dynamic set, which records the local connectivity for embedded states and the parameters that be used to express the transaction probability. To boost the sample efficiency, UVN uses a shared probability set, which is trained during the learning process. Then the question is how to get the optimal dynamic set. This can be treated as the estimation for random variables. The objective is to minimize the mean distance between the true value and the estimated value. We use a straightforward solution, clustering on the transaction probability. The dynamic set is built from labels, and the shared probability set is just like choice. UVN can be trained via both imitation learning and reinforcement learning. In imitation learning, expert trajectories are available to the agent. Thus, we could use the frequency of the transaction loops to estimate the transaction probability and compute P and D. With D known, we can compute the loss between output and optimal action. In reinforcement learning, the frequency of embedded dynamics can only be counted during the learning process, and the dynamic set D will be updated periodically by a clustering program. So then the network structure is dynamically changing during the weight optimization process, and we apply episodic Q-learning to train VUN in RL. Now let's talk about the experiments. We evaluated U1N with both spatially invariant and variant tasks, covering two domains, maze navigation and Minecraft. In maze navigation domain, we applied three types of maze with different transaction model, including regular, chessboard, and Mars. Regular maze is a typical spatially invariant problem. Results show that all the compared methods have a good performance, proves that U1 can effectively learn the transaction model without any prior knowledge. The other two settings, chessboard and Mars, are spatially variant environments. In chessboard settings, there are two types of grids, staggered like chessboard. In Mars setting, the transaction model of each state is generated randomly. The results show in these two spatially variant settings, U1 has the best performance, while other models fail. Figures visualize the map and corresponding value function for U1N, VNN, and G1N. The shape of value function of U1N resembles the original navigation map most truthfully, proving that U1N has learned the reward function and transaction function close to the original task. To evaluate U1N in more realistic domain, we designed synthesis tasks in Minecraft. In addition to getting the deserved inventory, if the agent's decisions result in an unwanted inventory, it will be penalized for them. We formalize the task as being hierarchical. U1N works at the top level to determine a sub-policy to be used. The input of U1N is the inventory state, and the input of sub-policy is the image. We set up both deterministic and stochastic environments. The state transaction probability can only be 0 or 1 in deterministic environments, and it can be a flow between 0 and 1 in stochastic environments. The results show that U1N solve all tasks successfully while imitation and reinforcement learning, while other methods failed. Finally, let's end with the video of validating U1N in Minecraft without X training. Thanks for your attention and thanks for the contribution of the co-authors. For further information, please contact us.